Hello, I'm Lisa Schwartz with Berkeley Lab. Welcome to the webinar on our recently published report on data, metrics, and analysis for grid resilience to weather events. Next slide. I'm joined today by co-authors Miles Collins, Mattia Whiting, and Josh Schellenberg. And we thank the U.S. Department of Energy's Grid Deployment Office for funding our study. Before we get started, just a few housekeeping items. All attendees are in listen mode only, so please use the Q&A box to enter your questions at any time, and we'll answer those questions following the presentation. Slides are posted to the project website. We'll put a link in the chat box, and we'll also post a recording of the webinar in a couple of days at the same site. Next slide. So for our agenda today, first, I'll cover our objectives and scope for the study, and then Miles will present on our methodology and framework. Next, Mattia will present on state requirements, vulnerability assessments, and hazard exposure. And Miles will return to get into some of the details on the data metrics analysis that we see utilities including in their resilience plans, as well as sort of the overarching findings of the study and examples of utility leading practices as well as state leading practices. And then finally, I'll moderate Q&A with webinar attendees. Again, please enter your questions at any time in the Q&A box. Next slide. So let's talk briefly about the motivation for the study and its scope and methods. Next slide. So states and utilities are working to improve grid resilience to address threats posed to electric systems from increasingly severe weather events. It's still relatively nascent at this point, and there's not yet an industry-wide consensus on what data, metrics, and analyses are most effective to improve utility decision-making related to grid resilience investments. So the objectives of our study are to help bridge the gap between the data metrics analyses that utilities use and the information that utilities provide to utility regulators, state energy offices, and other stakeholders that engage in the grid resilience planning process. We also hope that this helps utility regulators identify, describe, ask for, and use utility data analyses to help inform their own decisions on the utility's resilience plans, as well as cost recovery requests for the investments, typically in general rate cases. And we also hope to help stakeholders understand why certain information is needed, why it's important, and what exactly the utility can provide. Our study focuses on resilience to severe weather and climate conditions. So other hazards like earthquakes and cyber and physical security are really important, but for this particular study are out of scope. But this study builds on a report we published earlier in July that summarized state requirements for grid resilience plans across a variety of hazards. We also identified emerging best practices and provided a template that utilities and regulators can adapt to suit their own needs for resilience plan filings. So with that, Miles, why don't you take it away?
Thank you, Lisa. It's nice to be speaking to everyone today. To conduct the research for this report, the Berkeley Lab team reviewed resilience planning requirements for 15 states and one city. These requirements direct utilities to develop plans to address certain hazards. We reviewed the requirements to determine what data metrics and analyses must be filed, either as part of the plan or in supplemental reports. We also reviewed the resilience plans themselves to assess the resilience data metrics and analyses that utilities provided to regulators and stakeholders. These plans had a variety of names, in some cases reflecting the specific types of hazards they address, such as storm prevention plans in Florida and wildfire mitigation plans in Western states. Others, such as climate vulnerability assessments and resilience plans, covered multiple extreme weather threats. And some resilience plans are incorporated into broader planning filings, such as distribution system plans. We reviewed the relevant academic literature and reports from industry working groups. And finally, we conducted 9 interviews with staff at public utility commissions and state energy offices and subject matter experts at utilities throughout the country to identify common challenges and emerging best practices. The literature contains a number of resilience planning frameworks that utilities can leverage in their planning processes. These frameworks generally include an assessment of climate hazard risk or vulnerability and follow the key steps of evaluating electric system exposure to the hazard, sensitivity to the hazard, and expected consequences. They also typically include a prioritization process or selection method for potential mitigation measures based on the results of the vulnerability assessment and the expected cost and effectiveness of the measures. The figure here shows the overarching categories used in this study to organize the data, metrics, and analyses in the utility resilience plans. The vulnerability assessment category is at the top of the figure. This is a stakeholder informed process that identifies vulnerabilities to specific hazards and prioritizes vulnerabilities that are most important to mitigate based on potential impacts. Hazard exposure on the left comprises data on weather hazards and the exposure of utilities' assets or operations, and ultimately its customers to these hazards. Attribute metrics, the next category, describe system characteristics that contribute to the resilience of the system and community. For example, they can describe the extent to which assets have been hardened or mitigation measures have been implemented, and thus whether the electric system and its customers are sensitive to damage from a particular hazard. Performance measures characterize the impacts of resilience investments on system performance. This is often through a reduction in negative consequences of hazard events. So, performance metrics can include impacts to electric service, asset damage or failure, response and restoration effectiveness, monetary impacts, and customer communications. The vulnerability assessment category in the diagram spans across the three categories below it, as the information in these three categories aligns with and can inform the different steps of vulnerability assessments. The last category on the right, evaluation and prioritization analyses, covers methodologies that utilities employ to assess and prioritize resilience measures for implementation. Ex post studies or backward looking analyses estimate the performance of measures that have already been implemented. Ex ante studies or forward looking analyses estimate the future performance of proposed measures. And then prioritization analyses utilize different methods for selecting a portfolio of measures to implement. With that, I will pass it to Mattia to discuss state requirements.
Thanks, Miles. So I'm going to give an overview of state resilience planning requirements with an eye to the specific guidance around metrics, data, and analyses. Next slide, please. So to begin, in the last decade or so, really mostly within the last 5 years, we've seen an increase in the number of states that are requiring electric utilities to file grid resilience plans. So as of September 2024, which is our cutoff for this report, 15 states and 1 city, New Orleans, have some form of a resilience planning requirement for electric utilities. On the right, you can see a map of these states. Green states are those for which we've identified a state requirement and know that utilities within that state have filed plans. Connecticut, shaded in blue, has a state requirement for resilience planning, but utility plans have not yet been filed. And then the state requirement in Louisiana, shaded in purple, is still being developed. Next slide, please. So state resilience planning guidance may require utilities to address multiple hazards, or it may be scoped more narrowly to address a regionally specific extreme event like wildfire or severe storms. The table on this slide groups states by their plan focus. So up top, we have those that address a number of hazards, either through a general system resilience plan, a climate resilience and vulnerability plan, or an infrastructure modernization plan. Below that, we have the states that require utilities to file some form of a storm protection plan. And then below that, we have those that require wildfire mitigation or protection planning. So often, severe weather events catalyze legislative or regulatory action on resilience planning requirements, especially those that address specific hazards like storms or wildfire. An example of this is that after California had its devastating 2018 wildfire season, the legislature passed a Senate bill mandating that utilities file wildfire mitigation plans. We've seen something similar happen with extreme storms in states like Florida and New York. Next slide, please. So we looked at 5 categories of analyses and metrics, which are included as the main columns on the table on the right. These include vulnerability assessment, hazard exposure, prioritization and evaluation analysis, attribute metrics, and performance metrics. So this is evident when you're looking at the table, but of these categories, hazard exposure and performance metrics were mentioned in state guidance most frequently. We'll also note that utilities are typically undertaking hazard exposure analyses as part of their plan, and they're displaying data from these analyses within the plan itself. Performance metrics, on the other hand, are typically filed in a separate report or separate reports, often at a specified interval, quarterly, annually, after the plan has been filed. So they can help a utility gauge the performance of the resilience initiatives that are outlined within the plans themselves. So we went through each of these categories of analyses and metrics and state requirements with an eye for their flexibility and specificity. For example, the California CAVA requirements are required and specific across the board, as is depicted in that row of dark orange circles at the top. And what this means, for example, in the case of hazard exposure assessment, is that the California Public Utility Commission, the CPUC, has specifically outlined preferences regarding parameters for these analyses. These include climate variables, scenarios, and data sources. And I'll say it's pretty unique to see this level of specificity in state guidance. But also note that the benefits include standardization between plans and over time, and assurance that utilities are using the best, most up-to-date data. So other requirements may be a little bit more flexible. Take the Texas System Resilience Plans. Guidance on the metrics and analyses included in these plans is predominantly higher level, hence the lighter orange circles in the Texas row. So what this looks like, for example, with performance metrics, is that the commission requires utilities to provide metrics evaluating the resiliency measures that they propose in their plans, but it grants them agency to decide on the specifics of these metrics. The Public Utility Commission of Texas also grants utilities flexibility around characterizing and analyzing hazards and their impacts, which effectively allows them to design their hazard analyses in a way that makes sense for their specific region or their service area or their system. So these are just 2 examples, but our report basically walks through all of the state requirements with the same lens to better understand the ways in which they're approaching requirements around metrics, data, and analyses in these reports. Next slide, please. So now that we've walked through the state requirements for resilience planning, we're going to dive into the specific data, metrics, and analyses being included in the utility plans that we reviewed. Next slide. Thanks. So evaluating vulnerability to more frequent and severe weather events is essential for building a resilient plan. Regulators may prescribe specific steps for utilities to assess risks and vulnerabilities, or they may allow utilities to determine their approach themselves. Vulnerability assessments range a lot in their specifics, but they often focus on understanding key elements of hazard characterization, exposure, sensitivity, potential consequences, and adaptive capacity, as are listed on this slide. So these elements describe the magnitude and nature of relevant hazards, the degree to which assets are exposed to these hazards, both presently and in the future, the degree to which an asset may face adverse impacts when exposed to a hazard, and then the level of negative consequence on the larger system should the asset face these adverse impacts. Vulnerability assessments may also include components of community sensitivity and adaptive capacity, which basically capture the customer and asset's ability to adapt when exposed to hazards that they're sensitive to. Next slide, please. Thanks. Vulnerability assessments typically capture the components that I just discussed through a combination of qualitative and quantitative analysis. So some assessments will score assets based on thresholds of exposure sensitivity, consequence, and adaptive capacity, or they'll use something like a high, medium, low designation, which you can see in the RG&E and NICEAG example. So here are 2 diagrams, 2 of very many diagrams that we reviewed. just an illustrative set of examples that depict how these components are combined for PG&E on the left, and RG&E and NYSEG on the right in both of their climate vulnerability assessments. Next slide, please. So I'm going to talk a little bit more in depth about hazard and exposure data, because the way in which a utility identifies and tracks these data is key to its understanding of its vulnerabilities. So developing hazard data for a vulnerability assessment involves selecting variables, selecting future climate scenarios, choosing a time frame, and sourcing your data. Next slide, please. Here's a little bit more information about each of these elements. So to start, hazard variables. This involves both the selection of the hazards themselves, heat, wildfire, flooding, which is typically informed by regional climate patterns or by state guidance, and then the variables within these hazards, for example, something like days over 86 degrees Fahrenheit, or annual maximum temperatures, or maximum 5-day precipitation, and these are typically informed by relevant asset thresholds. So developing hazard data also requires a selection of future climate scenarios, and these are represented through RCPs and SSPs. Not going to go that deep into these in this presentation, but you can read more about them in the report. They essentially describe projected greenhouse gas emission trajectories and possible futures for our society. This includes economic growth, population change, urbanization, technological progress, the components that influence the potential magnitude of future changes in climate. So selection of these scenarios can be based on state guidance or on risk tolerance. The graphs in the upper row of figures on this slide, kind of a visual representation of these scenarios as they show a future range of conditions through the box plots and a shaded line. And really quickly, the two different colors of boxes show the two different RCPs, and the boxes themselves show a distribution of the global climate model data within each RCP. And same goes for the shaded line. It's basically, a range of potential futures. So utilities are assets with a lower risk tolerance, which is typically, especially in the case of assets, those with a higher consequence if they go out, often use a higher change scenario in their vulnerability assessment to kind of model a worst case scenario, worst possible condition, and ultimately, ensure that they are prepared for these conditions. So continuing on, the time frame for which a utility develops hazard data is typically informed by state guidance, asset lifespans, and data limitations. State guidance will sometimes specify the future time periods for which a utility must develop data. For example, the CPUC requires that California utilities develop data for timeframes of 10 to 20 years, 20 to 30 years, and 30 to 50 years into the future. Utilities may also decide on these timeframes with asset lifespans in mind. You're not going to conduct a vulnerability assessment for a present-day asset 80 years into the future if you're going to replace it in 50 years. And also based on data limitations. For example, the latest downscaled temperature and precipitation data for the US is projected out to the year 2100, so we're not working with projections past that year. Finally, utilities developing hazard data must decide on the sources for these data. So these sources may include, for example, large scope data sets, like nationwide, downscaled, gridded global climate model data, sorry, that's a mouthful, or more local data sets such as, event databases, or locally generated wildfire or flood projections. It's developed at a local level. Next slide, please. So exposure analyses basically take hazard data and they overlay it on company asset data. So you can do this kind of analysis using programs like GIS or R or Python, and it allows you to derive asset-specific exposure understanding to all hazards for which you have geospatial data. Exposure analyses allow utilities to determine which parts of their system are most exposed to hazards of interest and basically allow them to focus their resilience efforts. So here are two examples of maps that depict exposure data. Slide shows, if you skip to that. Um, Thanks. That these data can also be presented as graphs, tables, and summary stats. And so, here's again just a small handful of many examples that we reviewed throughout the utility plans. And I also know of a few utilities that are taking these findings a step further from their reports, and they're basically generating dynamic tools such as a digital twin model to better understand asset exposure to hazards more flexibly. So thanks. That's it for my slides. Handing off to Miles.
Thank you, Mattia. So, attribute metrics are characteristics that contribute to or describe the resilience of the system and community. They align with the specific definition of resilience. So, for this report, they would describe the ability of the system or community to anticipate a hazard, withstand the hazard, adapt to hazard impacts, and recover from the hazard to a normal operating state. These components are generally referred to as the phases of resilience. Utilities that carefully track attribute metrics can connect these asset characteristics with specific performance metrics. So, this slide depicts a common visual representation of resilience. The slide has three versions of this graphic from the literature and then one from a utility resilience plan. Each diagram shows system performance on the y-axis and time on the x-axis. There's usually a line representing performance starting on the left that dips down as the resilience event occurs and weather impacts the system. The line then eventually climbs back up as the system recovers. So the academic literature and the utility resilience plans have some variation in the definition of resilience and its phases. Now, these diagrams show some of those differences. So, for example, in the upper left, we have the phases of plan, absorb, recover, and adapt. In the upper right, we have anticipate, withstand, absorb, and recover. So while these definitions and phases may differ, the overarching concept remains largely the same between representations. This table shows the type of attribute metrics described in utility resilience plans for each of the four resilience phases. So, anticipated metrics describe the likelihood or characteristics of potential impacts caused by a hazard. So, what's the potential for hazards to damage assets, or in the case of wildfire, for assets to damage surroundings? They can also describe the ability of the system to track and identify hazards, such as through more robust weather forecasting and monitoring systems. Withstand metrics describe the electrical system's capacity to avoid being affected by a hazard. They include asset condition, ratings, or hardening status. Adapt is the ability of the grid to respond to asset damage or of the community to change behavior to minimize impacts to customers. So the metrics can reflect system redundancy, where backup systems or resources are in place to ensure that critical functions continue during a disruption. And they can also describe the ability of communities to minimize negative impacts of power interruptions. Recover metrics describe the ability of the utility to return to normal operation after hazard events through preparedness, accessibility, and power restoration. Investments in the utility's ability to recover from a disruption can increase the speed with which utilities can respond to these hazard events, repair the system, and restore power. This slide shows an example of an adapt phase attribute metric that Southern California Edison developed called the Community Resilience Metric. It measures the sensitivity and adaptive capacity of a particular community to an interruption. It uses 37 different indicators of community sensitivity and adaptive capacity, including health risks, housing quality, pollution burden, cooling center access, and transportation access. Southern California Edison calculates the metric at the census tract level with final weighting of indicators incorporating input from community organizations. The map summarizes results for the utility service territory at the census tract level, ranging from low community resilience in red to high in green. The results help inform prioritization of investments that mitigate climate vulnerabilities. Moving along to performance metrics, These metrics describe the effectiveness of resilience investments by quantifying the extent to which they have or have not reduced the negative impacts of hazard events. So, utility resilience measures seek to avoid some or all the negative impacts that would have occurred without the measures. Performance metrics measure the progress toward achieving these objectives. We have 5 different categories of performance metrics in this report. Electric service metrics describe power interruptions in various ways and using a number of different variables. Asset damage and failure covers impacts to assets. Response and restoration metrics describe the speed and effectiveness of utility restoration efforts. Monetary impacts reflect the cost of impacts to the utility, to customers, and to the regional economy. Customer communications and engagement metrics describe how effective utility outreach efforts are. These are important as utilities communicate about impending storms, interruptions, and public safety power shutoffs. Regulators, utilities, and stakeholders can examine performance metrics across additional dimensions by looking at critical infrastructure, public safety power shutoffs, and by looking at distributional impacts of the metrics. So I'll dig a bit deeper into some of these categories. First, electrical service. It's common to distinguish between grid performance under normal operating conditions and performance under abnormal operating conditions. But for normal conditions, utilities exclude major event days, or MEDs, which are statistically determined days when utility system performance is significantly impacted by events outside of normal operating conditions, such as extreme weather. MEDs were developed to enable year-on-year tracking of reliability performance that would otherwise be skewed by weather events that vary in number and severity from year to year. Standard reliability metrics are generally calculated and reported on an annual basis. In contrast, resilience is focused on notable events that occur at specific times within a year, like over a day or a week. And resilience events generally, but not always, occur during major event days. The table shows examples of metrics for electrical service. Many of them are reliability metrics that utilities have adapted for resilience planning by including MEDs for the year, or for using the indices only for times when there were major storms, which some states have as a separate classification for major event days. The metrics cover interruption events, customer minutes interrupted, frequency and duration of interruptions, and percentage of customers experiencing multiple or long interruption durations in a given time period. They also cover metrics that utilities or working groups have developed themselves. There are a few key dimensions of granularity for interruption data that can help in targeting electric service metrics. These are interruption start and end times, cause, and location. So IEEE standard 1782-2022 provides guidance for collecting, categorizing, and using interruption information. For example, it gives 4 data elements, which together can describe the cause of an interruption in detail. These are cause category, subcategory, affected equipment, and contributory factors. This structured approach to identify and categorize causes of interruptions can enable consistent reporting and analysis. This slide shows a segment of a wildfire mitigation data reporting template from the California Office of Energy Infrastructure Safety. And it illustrates the level of granularity on the detailed end of the spectrum for providing information on outages based on cause category. There's a subcategory called the risk event driver. There's the line type of transmission versus distribution, and then a high fire threat district here, so location. This slide shows the next 2 categories of electric service metrics or performance metrics. The asset damage or failure category covers metrics that utilities use to track the extent and characteristics of asset damage from severe weather events, the performance of assets during these events, and then the rates of repair and replacement from the events. For the purposes of this report, this category includes only the asset information and not the monetary impacts. Those are covered in a later category. For the response and recovery category, on the response side, we would have level of resource engagement, extent of mobilization efforts, such as crew deployments and efficiency. For restoration, The metrics focused on the time to restore a certain portion of customers, or also on the portion of customers restored given a certain amount of time. We also found examples of utilities experimenting with developing their own metrics to characterize restoration, such as National Grid, which measured restoration time between when the peak number of customers were out and the point at which 95% of the customers had been restored. The monetary impact metrics are in three categories here. So, first is utility costs, which could be capital or operations and maintenance. It covers the monetary impacts from damage from resilience events, as well as operations and maintenance costs from restoration activities. Customer interruption costs are those incurred by customers experiencing a power interruption. Berkeley Lab has a tool called the ICE calculator, used by a number of utilities across the US, which aggregates customer interruption cost studies that have been conducted across the country and provides estimates of costs for interruptions shorter than 24 hours. The customer interruption cost studies are conducted by surveying residential, commercial, and industrial customers and utility service territories to determine the costs that they incur from power interruptions. For widespread, long duration interruptions lasting more than 24 hours, we start seeing spillover effects, where, for example, an interruption to a manufacturing facility impacts all of the customers of that facility who would not be receiving the goods it would produce. And for these types of interruptions, we can use macroeconomic models. One example of this type of model is the prototype Power Outage Economics tool, or POET, which is developed and piloted by Berkeley Lab and partners, including Commonwealth Edison in Illinois. And it uses a hybrid valuation approach with customer interruption cost surveys to collect information on household and business customer behavior, and then use the data to calibrate a macroeconomic model of the regional economy. So the bar chart on the right shows changes to gross domestic product from interruptions lasting 1 day, which is in green, 3 days, which is in yellow, and then 14 days, which are the larger bars in red. Resilience plans also often look closely at performance metrics in terms of specific types of infrastructure, specific groups, and then types of interruptions. So one type of infrastructure are critical facilities, and these are facilities that are essential for the health and well-being of the community and include things like hospitals, fire stations, water treatment facilities. We see plans focused on that are focused on wildfire mitigation, and these will also often look at public safety power shutoffs. So these are when utilities intentionally de-energize portions of the grid to reduce the risk of wildfire when the combination of wind and other environmental conditions creates a high risk of fire. Resilience plans also assess the distributional impacts of performance metrics, so they'll often focus on disadvantaged or vulnerable communities to see if they would see a proportionate share of the benefits of the resilience improvements. The map shows census tracts of disadvantaged communities here as determined by states in New York and Los Angeles, respectively. The last category in our framework covers evaluation and prioritization analyses. This category includes ex post analyses, which compare the performance of the electric grid before and after implementing resilience measures. In an ideal ex post analysis, researchers would be able to control for various factors like weather that can impact system performance in order to isolate the impact of the resilience measures. This can prove challenging for resilience events, but we see more and more utilities aiming to do it. Ex ante analyses are forward-looking and estimate what the impacts would be from implementing resilience measures. They often leverage information learned in ex post analyses to predict what that future performance will be. And then prioritization analyses include various methods for determining which measures to implement and how to prioritize them within the budget constraint. This slide shows 3 examples of ex post analyses that were in the resilience plans. DTE Electric is in the upper left. They analyzed the impact of a short cycle maintenance program that identified circuits with characteristics that make them prone to storm-related failures. It looked at SAIFI, SAIDI, and all-weather SAIDI before and after implementation and saw reductions in all 3 metrics. Florida Power and Light analyzed the impact of its distribution and transmission inspection programs on the upper right by comparing performance of distribution poles and transmission facilities during Hurricane Wilma, which was before the program, to performance for Hurricane Irma, which was after implementation. They saw more customer outages, but fewer poles needing replacement and faster restoration times. Portland General Electric implemented safety-adjusted protection settings on devices within a high fire risk zone to reduce ignition risk during the fire season. To analyze the system-wide reliability impact of this, they conducted an ex-post analysis to compare SAIDI, SAIFI, and MAFI during the wildfire season in 2019 and 2020 with the seasons after implementation, so 2021 and beyond. They found slightly longer interruptions during extreme weather days, but they found that this had a negligible impact on the reliability overall. The table on this slide shows the key methods or analysis categories that utilities use to select and prioritize investments. It includes benefit cost analysis, or BCA, which calculates the present value of monetized benefits and costs, and can use the benefit cost ratio to prioritize measures. Risk-based analysis estimates cost effectiveness using risk reduction benefits and can rank measures based on a risk spend efficiency or the normalized cost of risk reduction. Multi-criteria assessment, the third one, is useful when certain benefits are difficult to quantify and generates composite indices using scores and weighting for each criterion. The chart on the right shows an example of BCA for United Illuminating for 9 priority distribution circuits. The first 3 bars show the cost of implementing 3 different types of measures or proposals on all 9 of the circuits. The lines show the benefit cost ratio under 2 different storm scenarios. And you see that the ratios are below 1 for each of them, indicating that costs are greater than benefits. The optimal set on the far right selects the proposal with the highest benefit cost ratio for each circuit. And here we see that the benefit cost ratio for this set increases to above 1 for both scenarios. Moving on to key findings and emerging best practices. The key findings. First finding, resilience planning is difficult and presents a number of challenges. It's also relatively new. So among the challenges are that severe weather events are infrequent and hard to predict. Events or effects are experienced unevenly across the territory. The measures are expensive, but may never be put to the test by an event. And resilience planning requires considerations that extend beyond traditional reliability planning, such as health, safety, community well-being, and critical infrastructure. So it presents challenges for utilities, regulators, and stakeholders, but we see they're taking steps to address them. While the approaches to risk and vulnerability can vary in nomenclature, they will tend to have a similar framework. Utilities and regulators acknowledge the need to augment standard reliability metrics with metrics tailored to measure resilience, as traditional system-wide reliability metrics alone don't capture the complexity of resilient utility systems. And utilities and industry working groups are developing more indices for characterizing resilience attributes and performance. Furthermore, utilities and states we see are defining and considering vulnerable populations and looking at performance metrics. We also see them taking steps to measure and track performance of resilience measures over time. One challenge that remains is that we discussed a bit is how granular data is helpful for measuring performance, but regulators, stakeholders, and smaller utilities even face a trade-off between more data and having the limited resources to analyze and interpret it. So, although resilience planning is relatively nascent, we see a number of emerging best practices from our research. First, select or establish a clear analysis framework. So it's important for regulators and utilities to have a mutual understanding of the resilience planning framework, which guides development and sharing of data metrics and analyses to support the planning process. Second, consistent definitions and accurate location data for critical facilities. So utilities already prioritize restoration activities and coordinate with emergency management agencies to ensure critical facilities remain operational. A standardized definition of these facilities between utilities in the same jurisdiction can help regulators and other state agencies coordinate with the multiple utilities, and it can facilitate comparisons of critical facility related performance metrics between utilities in the same jurisdiction. Vulnerable populations. So, developing a more thorough understanding of these populations and their capacity to adapt to power interruptions of varying durations enables more effective strategies for reducing negative impacts, such as where to locate resilience hubs. Measuring impacts consistently and at a granular level. So I discussed this one already, but outage management system data contains a wealth of information about the causes and locations of interruptions, as well as affected equipment. It can be a very useful planning resource, particularly if it's standardized and consistent. Addressing uncertainty. So there's a lot of uncertainty in planning for low frequency, high impact weather events, and novel ways to address it and communicate it can help the planning process. Examining large numbers of hazard impact scenarios can provide a more comprehensive assessment of risk. It can enable utilities to evaluate resilience measures and strategies that perform well over a range of plausible future scenarios. Using combinations of metrics. So major interruption events from severe weather can be viewed as frequency distributions with interruption duration on the x-axis per customer and frequency on the y-axis. Metrics that reflect system or circuit level averages like SAIDI are useful for understanding the mean of the distribution, including other metrics that measure the portion of customers experiencing long interruption durations of various lengths can reveal the length of the tail of the distribution and the portion of customers impacted over time. And finally, ex post analyses, we discussed that these are improving. They tended to be ad hoc, limiting the comparability of results across regions and years. An emerging opportunity is to conduct ex post analyses more systematically on a regular basis, including with the use of statistically representative comparison groups. This concludes the presentation portion, and we can now move on to Q&A.
Great. Thanks so much, Miles and Tia. And we've got some great questions, so I'm going to dig right in. I'm going to start with a question from Tia. What is the scope of the plans? Are they mostly limited to power generation and distribution system, or are they incorporating in some way end-use loads like homes and businesses to help utility customers protect themselves? For example, storage programs, solar plus storage, that kind of thing.
Yeah, absolutely. So the bulk of these plans typically covers power generation, transmission and distribution systems, and operations and services within the utility. But some states require a more community-based section. For example, PG&E's Resilient Together initiative, which basically integrates community feedback, discusses potential impacts of hazards on communities, dives into adaptive capacity. And it's usually through a section like this or through a broad section of adaptation recommendations that something like customer energy storage or solar and storage programs is included in plans. For example, a section detailing recommendations to allow customers to be more resilient in the face of hazards.
Great, thanks. I have another question for you, Josh. Miles, if you can go to slide 16. This was an anonymous question, so I wasn't able to check back with the person asking the question. But the question was, can you explain the difference between top and bottom for California? And I think it refers to this slide. We're not sure if it refers to the whisker graphs at the top or explaining the difference between the graphics at the top of the slide and the bottom. So can you sort of address all of that quickly?
Sure, I'll do my best. So the box and whisker plots and the line graph next to them show the two RCPs, RCP 4.5 and 8.5, RCP 4.5, shown in yellow, I think on both graphs, represents a more moderate emission scenario and less intense warming. RCP 8.5 represents a more unabated emission scenario and therefore shows higher warming. You can see that these graphs, and I should have made the legends larger, but they're showing temperatures. I believe they're both showing temperatures in Central Park. They're from Con Edison's Climate Vulnerability Assessment. And so within each RCP, there's a number of global climate models, around 30, depending on which version you're using. And these models all show slightly different projections. And so these are, captured as an ensemble in a chart like this box chart. It's showing the quartiles of the model outcomes, or in the line graph, which shows them through this shaded section. And so, like I said, the two figures on the top are representing temperature, and the two figures on the bottom are completely different, representing inland flooding using the FEMA floodplains. The one on the left is a region of PG&E's service area, and it shows through a blue and orange floodplain the FEMA 100-year flood and the FEMA 500-year flood, just the extent. That's the raw data that you get from the FEMA portal. And then the map on the right is ONR, they're upstate New York. And they took it a step further, really cool analysis, interpolated between flood elevations and added a digital elevation model to basically get flood depths throughout the floodplain, which is taking, the raw data a step further. But all showing very different things, except for the two on the top are showing something very similar, which is temperatures.
Great, thank you. Here's a question for Josh, who didn't present today, but is a co-author of the report. Josh, how do you calculate benefits from resilience measures when those assets or areas don't experience an outage during a major event? In other words, how do you measure something that didn't happen, especially when major events can be so drastically different?
Yeah, that's a good question. In this case, I was looking at the question and I was thinking it's referring to like after an investment is made and you want to measure those benefits. And yeah, it's challenging to estimate what those benefits would be if you don't have a major storm that comes through to test that the investments that were made are effective at increasing resilience during major storms. So in some cases, you might be able to look at, slightly less extreme events and potentially extrapolate a little bit or compare to historical performance in maybe not the worst case type scenarios, but slightly less than that. But yeah, it is a challenge. By definition, resilience events are rare, and so as investments are made, it becomes more challenging to estimate those benefits after the fact. If you have to wait for a major storm to really know for sure that the investments delivered those benefits when they're needed most.
So Mattia and Miles, you want to jump in here with any additional reactions?
Yeah, you can. Ideally, you're looking for some control group to compare. To compare it to, whether it's for, let's say you put an investment on a set of circuits, and you're looking at the you're looking at performance in the past. You can also look at performance on similar circuits that may have experienced the storm. In the absence of a storm, you can also you can estimate a reduction in risk by looking, either at other utilities that have implemented the measure, or within the same service territory at the same utility. But it definitely presents a challenge, and looking to get creative to either look for control group or reducing the risk.
Sorry about that. Okay, so let's move on. We have a question about providing locational data. Have utilities expressed concern about providing locational data for critical facilities or their determined vulnerabilities. For example, how can they address these concerns through confidential filings?
Yes, I think in speaking with commission staff and state energy office staff and utilities, there is that a balance that needs to be found between uh, the data that is being able to look at performance and also being able to keep the location and information about these critical facilities um, confidential to a certain extent. So these can be, they can be in confidential filings, like the specific locations of the critical facilities, information about performance and accessibility can be aggregated and to a certain extent, aggregated to a certain extent, so that you can look and understand the performance during resilience events. Without necessarily knowing where these specific facilities are. So they did raise those concerns, and they did mention that there is there's a level of data that is acceptable for utilities and perhaps regulators to see, whereas you wouldn't show those to the general public or a number of stakeholders.
Okay, let's move on to several more questions, and let's try to get through a lot of these quickly. This next one is, do the plans offer information on the way that utilities are training their personnel?
I can take that real quick. It does vary a lot. As some plans are very capital focused, where others are including operations or maintenance, which I would think includes training in many cases. The big, I guess, exception to that would be the California wildfire mitigation plans, which have a major safety culture assessment component to it, to really that really focuses on the staff and the leadership and the lines of command, and ensuring that everyone has training related to risk and safety.
Mattia, Miles, anything to add there? All right, let's move on. This is a great question. Are there any examples of RTO-wide guidance for reporting and measuring resilience? Anybody aware of that?
I'm assuming it needs like our ISO/RTO type, but organized markets, right?
Yeah, well, the
Yeah.
regional transmission operators or
Yeah,
the
yeah, yeah.
system operators, yes.
Yeah, it's interesting because when you look at the ISO RTO type planning processes, they don't really use the word resilience much at all. They just call it reliability, because just about any type of outage that occurs at that level is a resilience event in a way. So there are a lot of definitions around resiliency, like 1 in 10 type standards that need to be met, that are just called reliability standards in their case. So it's not, I don't think they have like a separate resiliency focused area to this point, but there are new approaches that are evolving to try to incorporate extreme weather risk in particular, both due to heat waves as well as um, cold weather, which was a big issue in recent years when there's been those polar vortexes that have impacted a lot of the ISO RTO type areas.
All right, so this sounds like an area that is ripe for additional work. I think.
Definitely.
Great. Let's move on to another question. So, Mattia, how do we achieve some level of standardization or enable benchmarking against utilities plans? There's so much variation in utility service areas, the different hazards, the systems, the planning priorities. So, what can we do with respect to that?
Yeah, I think you can do a few things. To start, I think we could develop kind of a core set of resilience metrics, and kind of require that utilities measure these across the board, and then supplement with additional system or regional specific metrics. I also think, someone mentioned this already, but like normalizing where possible, put the events in the denominator. Basically, you're dividing by events, to ensure that higher event years, and that's a sort of oversimplified way of saying this. There are much more complicated, ways of actually calculating this, but broadly dividing by events and having, higher event years, ensuring that they don't inaccurately, indicate something like lower resilience. And then just better collaboration between state regulators and utilities across state lines, and better data sharing and just like more conversation about this, I think could be, really, really effective.
Great. Let's move on and talk about performance metrics. I've heard this a lot that, look, performance metrics are, that utilities' performance are tied to things outside of their control, like extreme events. A utility might look maybe less resilient in a year with multiple extreme storms when you compare to a year with no extreme storms. So, how do we reconcile that and get useful performance metrics reporting from the utilities to be helpful here?
I can start with that one. Again, I would say, normalizing performance scores by events. And I think it's National Grid, and maybe Miles, you remember, we were looking at one utility that has a metric, something like this, that I think they measure something like event magnitude and time for outage restoration, something that basically, is cognizant of the context of the size and number of resilience events and captures that within the metric, again, to not inaccurately convey the system as less resilient because it happens to encounter a year with more resilience events. And Miles, maybe you have something to add to that.
Well, yeah, and I want to get to another question. So,
Okay, all right.
any additions? All right, I'm gonna go back to a question that we had earlier. It's been clarified that maybe we can go to slide 10, Miles. And California is listed twice in this table. So it's listed at the top and then it's listed again. So at the top, it's like an ensemble of hazards. And at the bottom, it's wildfire. So sort of asking for some differentiation here. What's covered under one versus the other?
Yeah, the top California requirement is the climate vulnerability assessment and risk-based decision-making framework. So we were reviewing the requirements for those, and just again with an eye to the 5 components that are within the table. And then the California under the wildfire section is for the California wildfire mitigation plans, which are filed separately.
Great, thanks. I wanted to ask this really great question, and we have 2 minutes. How do you see AI, artificial intelligence, playing a role in utility resilience planning?
I can take this one. We did see some but experimenting and using of it. One example is Avangrid is using it to gain a better understanding of their grid performance, both during calm and also during storms. I think their tool is called GeoMesh, and it looks at breaking down the service areas into smaller sections and analyzing lots and lots of data points like wind speed and precipitation, along with interruption history and vegetation density. And so they're looking for those, looking to use machine learning to identify those areas that need upgrades and to determine what the impact of weather on the system is to help predict future performance.
Great. Well, we're at time. We could talk about this for hours, all of us. Very interesting topic and so important. I want to thank Miles Collins, Mattia Whiting, and Josh Schellenberg, co-authors with me on a report for the U.S. Department of Energy's Grid Deployment Office. Thanks very much. And we look forward to talking with you all soon. Thank you.